Electrophilic aromatic substitution, part 2. Now that we know how to generate electrophiles, you can't do this on a test. See previous activity. You can't do that. But in that activity, you generated this electrophile. Okay? And you also made some OSO3H negative. You want a reminder? We were here. You made this react with that, and I didn't write it, but you do get OSO3H negative from that mechanism you showed. There it is. So you would redo that mechanism. Please don't write anything you write. You say, do it. And I'm going to use that combination on every example here. And I'm not having luck with this lately. Yeah, that happens every time. Well, you know, I need you. And I need you to be back to where you were. Oh. There. So, question 1. You got to pick the right pi bond to attack your electrophile. The right pi bond is benzene. So if you're going to put a group on the ortho position, you better use a pi bond that is attached to the ortho carbon. There's 2 candidates here. This ortho position has a pi bond. That one, you would use that one if you wanted to do the mechanism on that ortho position. If you want to do the mechanism on this ortho position, use this pi bond. There's no right or wrong here. You can use either one. Just looking at where I drew the nitro, I'm going to use this one because it's right there. Okay? But you could use the bottom one. So, talk to me. What atom are these pair of electrons going to attack? Nitrogen. What's going to happen to the pi, one of the pies? It's going to become a lone pair. I'm just making these pies look a little more like a pi bond here. And the pi breaks, becomes a lone pair. And you're not done. You're going to have a reaction going to an intermediate. Sideways benzene, not my favorite. Okay. You have NH2 here. You've got a pi there and a pi there. You got an old H here. And you got an NO2 up there. We'll put it in blue. We're using blue. Blue. NO2. You can write NO2 if you want. There it is, NO2. That's what it looks like in its full, well, all of its charges. The average is no charge, so you can write NO2 as a short form. And I got to remind you, yeah, there was an H there. And what happens to a carbon that now has 3 bonds that used to have 4? What do I have to put near this carbon? Lost charge. Carbocation. Put in green. What's going to grab that H and make this thing aromatic again? Yeah, the OSO3H. The step's called re-aromatization. Are you surprised by that name? It's becoming aromatic again. And OSO3H minus is picking up that proton. Sigma becoming pi, end of story. Very small arrow. But it was a good arrow. Yep. So we're going to talk about the meta scenario. There's only one pi bond. Well, there's two pi bonds in the molecule that touch the meta position. This is meta here. This is meta here. Which one did I pick for my product? The top one. They're both meta. So pi attacks. Sigma, pi becomes lone pair. Purple. And intermediates would run purple. Double bonds are still here and here. The meta position has an H here. There's a cation here. And NO2 went there. And what happened to that to finish it off? Same story. It's always the same story. The rearomatization grabs the H from the original carbon that got a new group. And it's back to having just three things attached and rearomatization. Wow, that was 2 words, huh? Not gonna give me the other part of the word? Could have written it by now. There you go. Good. And then make it smaller. There's only one pair of electrons that touches the pi. So you're going to start the mechanism, the para positions here, right? Para. Got to use that pair of electrons again, but it's directing the group to the para position. Purple arrow. H2N. Wow, why'd you do that? Para position has an H, has a new NO2. Cation's up here this time. Old pi, old pi. Same story. Done. So the mechanism is not very hard, is it? That's basically the whole chapter, like 90% of the mechanisms here. We'll only do electrophilic aromatic substitution today. And then in less than a half hour on Monday, we'll do nucleophilic aromatic substitution, and chapter 21 will be done, or 22 will be done. 2 short chapters. But we're not finished with this yet. There's a lot of explaining to do. What I'm going to do is redraw every cation, because I hope you understand why the first step is the slow step every time. Can you tell me why? The main reason why the first step is much slower than the second step, which would be really fast. Can you tell me why? What's being ruined in the first step? The special kind of resonance. What's the name of that special kind of a resonance where there's 4n plus 2 pi electrons rotating in a circle? Starts with A. Aromaticity. Yeah, you're losing aromaticity. This is not cool. That's very unstable. So slow. Reactions that make unstable things are slow reactions. End of story. Okay? So to compare these reactions, we need to look at the product of the slow step and ask ourselves, which of those is the best? Which cation is the best? So I'm just going to copy them. You got your ortho situation, you've got your meta situation, and you've got your para situation. Just going to copy the cations that I see already on the screen. Yeah, NH2. Put that lone pair on there. And we got H and NO2. And the meta cation, I'm just going to copy it right above. Should be easy to copy. And NH2. And the para cations to the left. Yeah, I wish that bond was a little longer. There it is, it's longer. Okay, copying para NO2 H, and I want to just do this, and I want to do just this, and I can't do that for the middle one. Can't do it. Arrows can't end up at the cation with the meta situation. Try. Can't. Not with a nitrogen lone pair. Hey, octet's full. Isn't that a good deal? Octet's full. Octet's full here too. So can you tell me which of the two scenarios is going to be the best? There's three scenarios. They have names. Ortho, meta, para. Para's the best. And ortho is, well, don't let my mistake trick you. There's a charge. Okay, don't be going there. Yeah, I'm glad she brought it up though, because I saw my mistake as soon as she said it. Wait, they should have the same charge situation, and they do, right? Okay. So why did you say para? It's good. I like it. Para is a little better than ortho, but they're both good. That's my big message for you. Ortho and para both can create an intermediate that has full octet. But if you go meta, you can't do that. So para is going to be major, and this will be minor, but it can sometimes be very close to 50-50. So this is the method to make ortho or para. Okay? And because the reactant is so cheap, I mean, we don't care if we're wasting half of it to make the products. If you need the ortho, do the reaction, separate the ortho from the para, you're done. Same story if you need the para. Do the reaction, separate the ortho from the para. There's your para, use it. Throw away the ortho, sell it to somebody, I don't know. Depends on which one you need. If you need the meta, you're out of luck, because meta is not going to happen. So, what kind of group needs to be on benzene to make ortho and para the major product? Groups. Here's the story. Groups on benzene that have a lone pair on the atom attached to benzene, which is true here, right? And we say are called ortho para directors. Ortho/para directors. And just keep in mind, para major, for reasons we haven't even talked about. That's how we're going to finish this exercise. You're going to tell me why you think para was a little higher in number or percent than ortho, and it has to do with not the cations themselves, but the approach of the NO2 to the benzene. Which approach has less hindrance with the NH2 group. Not the ortho where it's coming in as close to the NO2 as possible. Yeah, here it's bumping into the NH2 if it comes from the left side, right? We don't like it. No, it's not. No, it's about approachability. It has nothing to do with stability. The two products here, the cations, are equally stable because of the resonance. So you can't answer the question, why is para major and orthos minor using that? It has to do with when the NO2 was coming in towards the benzene, which NO2 had a clearer path, coming from ortho, where the NH2 is right there, bumping into it, or para, where the NH2 is nowhere around. That's the answer. Steric hindrance makes para slightly major and ortho minor. Major. Steric hindrance avoided. Minor has steric hindrance. When I say steric hindrance, we're talking about the approach of the NO2 group in the first step. Okay? Yes, hindrance is ugly looking here, but it's the same word over there, so we're okay. And that's that. Next activity, we're going to switch NH2 to a different group.